In this lecture, we use a table of standard reduction potentials and half reactions to write chemical equations and determine the cell potentials. As our first example, we examine the reaction that occurs when lead shot is added to a solution of silver nitrate. First, we must identify the oxidant and reductant and find their half reactions in the table. The problem gives three possible reactants: lead atoms, silver ions, and nitrate ions. Lead must be a reductant. However, both nitrate and silver ions appear as oxidants in the table. But the half reaction involving the nitrate ion requires an acidic solution. It is the nitric acid half reaction. There is no acid present here, so we can rule out nitrate ion as the oxidant. Therefore, silver ion is the oxidant. We then rewrite the two half reactions. In the second step, we determine whether or not there is a reaction by observing the relative positions of red and ox. We note that the reductant, lead, lies above the oxidant, silver ion, so they do indeed react. In the third step, we determine the standard cell potential as E0 cathode minus E0 anode. Ox is reduced in the reaction, so its standard cell potential is used for E0 cathode. Red is oxidized during the reaction, so we use its standard cell potential for E0 anode. In this reaction, silver ion is reduced to silver, so E0 cathode is plus 0.80 volts, while lead is oxidized to lead 2 plus ion, so E0 anode is minus 0.13 volts. E0 cell is then plus 0.93 volts. The positive sign also indicates an extensive reaction. All half reactions in the table appear as reductions, so red is a product. But red is a reactant in the desired reaction. Therefore, we reverse the reductant half reaction to make red a reactant in the fourth step. In this reaction, lead is a reactant, so its half reaction must be reversed. In the fifth step, we assure that electrons gained equals electrons lost. Silver ion gains 1 electron, but lead atoms give up 2 electrons. However, the number of electrons gained by the oxidant must equal the number given up by the reductant, so we multiply the silver half reaction through by 2. Each half reaction now involves 2 electrons, so the net equation involves a 2 electron transfer. In the last step, we simply add the resulting half reactions to obtain the net equation. Note that the electrons gained must always cancel the electrons lost, so the electrons never appear in the net equation. In the remainder of this lecture, we write net equations for the following. Select the button next to the reaction you would like to view. Metallic copper is added to a solution of nickel sulfate. First, identify the reactants. The mixture consists of copper atoms, nickel 2 plus ions, and sulfate ions. Recall that sulfate ion is a common counter ion, so it is a spectator ion in this reaction. Therefore, copper is the reductant and nickel 2 plus ion is the oxidant, so we copy their half reactions. Next, determine the reactivity. The reductant is below the oxidant, so there is no reaction. Copper does not react with nickel 2 plus. Electrons do not transfer to a less positive potential or uphill in energy. The galvanic cell reaction that occurs between a zinc 2 plus zinc couple and a nickel 2 plus nickel couple. First, we identify the two half reactions. Galvanic cells are spontaneous, so they require that the reductant lie above the oxidant in the table. The zinc couple lies above the nickel couple, so zinc is the reductant and nickel 2 plus ion is the oxidant. Zinc is oxidized to zinc 2 plus, so E0 anode is minus 0.76 volts. Nickel 2 plus ions are reduced to nickel, so E0 cathode is minus 0.23 volts. E0 cell then is determined to be plus 0.53 volts. To write the net equation, we reverse the zinc half reaction to make metallic zinc the reactant. The number of electrons lost by zinc is 2, as is the number gained by nickel 2 plus, so the reaction is a 2-electron transfer. Adding the two half reactions, we determine the net cell reaction for the galvanic cell. Sodium metal is added to water. Water appears in two places in the table, once as an oxidant and once as a reductant. However, sodium appears only as a reductant, so we choose the water half reaction in which the water is an oxidant. We then copy the two half reactions. The reductant is above the oxidant, so sodium does react with water. Water is reduced, so E0 cathode is minus 0.41 volts, and sodium is oxidized, so E0 anode is minus 2.71 volts. E0 cell then is determined to be plus 2.30 volts. We next reverse the sodium half reaction to make sodium a reactant. Sodium gives up 1 electron, but water requires 2, so we multiply the sodium half reaction through by 2. And then we simply add the two half reactions to obtain the net chemical equation. Zinc is added to hydrochloric acid. Zinc is the reductant, and a strong acid is the oxidant. Recall that the She half reaction at 0 volts is used for strong acids other than nitric acid. Copy the two half reactions. Check that there is a reaction. The reductant is above the oxidant, so electron transfer to the more positive potential or lower energy of the proton. That is, the electron transfer is spontaneous. Determine E0 cell. The acid is reduced, so E0 cathode is 0 volts. Zinc is oxidized, so E0 anode is minus 0.76 volts. Thus, E0 cell is plus 0.76 volts. Reverse the zinc half reaction to make zinc a reactant. Both half reactions involve 2 electrons, so electrons gained equals electrons lost. Add the two half reactions to obtain the final chemical equation. A copper penny is added to nitric acid. First, identify the appropriate half reactions. Copper is the reductant, and nitric acid the oxidant. Copy the equations. Note that the reductant lies above the oxidant, so there is a reaction. Copper is oxidized, so E0 anode is plus 0.34 volts, and nitric acid is reduced, so E0 cathode is plus 0.96 volts. E0 cell then is 0.62 volts. Next, reverse the copper half reaction to make copper a reactant. Each copper atom gives up 2 electrons, but each nitrate ion requires 3. The lowest common multiple of 2 and 3 is 6, so the copper half reaction is multiplied by 3 so that it produces 6 electrons, and the nitric acid half reaction is multiplied by 2 so that it requires 6 electrons. Thus, the net reaction is a 6-electron transfer. Add the resulting half reactions to obtain the net chemical equation.